Well, another fine mess I've gotten myself into. So I have a couple of really nice bass guitars, and no, I'm not really a bass player. I'm kind of a person who likes to play a bass guitar. I know that sounds strange, but you know what I mean. Anyways, I do like playing the bass once in a while when I get a chance, and I'm not very good at it, but it's just fun. And you know, I have a crate B160 bass amp, and I have a little practice amp, cheapy. But I really want a nice vacuum tube, tight sounding, non-distorting bass amplifier. And I've always wanted to build one. I do have a guitar amp that I built a long time ago, not the one off the videos, but it's based on a Fender AB763 circuit, modified a little bit. But it sounds really nice, and it actually sounds good with a bass, but it's, even though the front end of it's really not designed for a bass. So this one's going to be from the ground up. But as fate would always have it, you never have the parts that you need for the ideal situation. And I really don't want to spend money on transformers and things, because the transformers are just super expensive. Alright, I just got a call, and I like those kind of calls. Kind of really off subject of this video, but my sister-in-law just called. She was at a flea market, and she found a really nice, real old DeVry Institute old-fashioned oscilloscope, real cheap. So she picked it up, and I think maybe that'll make a nice restoration video here in the future. So anyhow, good deal. So back to my conundrum. So I want to build a bass amplifier, and I do not want it to, I don't play in bands, I don't play out anymore, I don't do any of that sort of thing, but I do want a nice practice amp, which means I don't want it to have to crank the volume up to get the sound that I want out of it. I want it to be a lower power one. I don't want it to be 5 watts, but in the same token, I don't want a 600 watt bass head. Not what I'm looking for. So the first thing I have to start with is, really, you're kind of limited by the transformers that you have available for the project you're going to build. And I want to build an amp that's using a really common output tube, like a 6L6, which is kind of what I want to do, or a 5881, which is a little lower powered version of the 6L6. And in order to do that, you kind of have to stick with the limitations of those tubes. And if you go to the tube manuals here, move this out of the way, 6L6 GC, and of course we're going to do a class AB push-pull. And just looking at some of the things here that we're looking at, you have your basically your recommended setups, and there's a 6L6, which is the older version. They're a lower powered, they're kind of similar to a 5881, and you have the 6L6 GC, which is the most common guitar amp tube that you see out there for that. And as you notice, here's the main thing we're looking at, is the load resistance for your output transformer. That kind of dictates, as you change the load resistance of the transformer, it changes the voltages that you have to have. And if you look at the 6L6, their typical operating ranges, there's 450 volts on the plate with a 5600 ohm or a 5.6K ohm plate resistance. So, and that's plate to plate. So it got me to thinking, let me go through my transformers that I have and see, first of all, we need a transformer for power that can give us, one of these voltages. And then we need, ideally, we want a transformer that can do this and an output transformer that can do this. But, you can't always get what you want. You got to work with what you have. So here's before me what I have available. I have this monstrosity power transformer, and it's 800 volts center tapped. Now that's 400 volts from each side of the center tap, and for the secondary. And if it does not have a 5 volt filament tap for a rectifier tube, because this is really kind of designed for a solid state high current rectifiers. Now I do have hex-fred rectifiers. The problem is when you do the math on this, you end up, this transformer ends up producing a little over 500 volts when you use solid state rectifiers, and and you're not getting crazy with chokes and all kind of stuff like that. That's too high for a 6L6, and plus for a little 30 to 50 watt amp, way too much. I mean, it's a 20-pound transformer. It's huge. 465 milliamps of current. It's just way too much. On the other side, I have this power transformer, and I have a couple other little ones, but they're not anywhere near what we need. This one is closer, but it's the opposite problem. It has 550 volts center tapped. It's really more well suited to a 6BQ5, the smaller pentode tubes, because what this is going to come out to is probably about 370, 380 volts, which is a little bit low for that 450. And really, once you load it down, it may even drop a little more than that. So, this is going to give me not quite enough voltage. This is going to give me too much voltage. I'm going to go with this one, and that's going to kind of, now it has to fit in with the output transformer. So what I have here, I have two of these, and it's really the only big transformers I have available right now, and they're kind of, they're rated at 100 watts, but you have to watch how Hammond sometimes rates some of these. Unless they're high-end transformers, when they say it's 100 watts, that doesn't necessarily mean it's 100 watts all the way through the frequency spectrum from 20 hertz to 20 kilohertz with very low distortion. Usually these ones, really, you want to run these lower than they're rated to get a nice clean flat response curve. So this is ideal for an amp that's in the 50 watt range, in my opinion, if we do the right things with it. Now if you notice, it's supposed to have a 5,000 ohm center tapped input, primary, okay? And that primary is about 5K if you connect these terminals to the correct loads, okay? So basically every transformer, output transformer, every transformer has a turns ratio and an impedance ratio. And if you connect things differently than this, you can actually make this transformer have a different input impedance or plate-to-plate impedance to the tubes, depending on how you connect the taps to the speaker. So depending on what impedance of speaker you're using on which output taps, it's going to affect, you're not always going to have that 5 kilo ohm input, okay? So let's, rather than just talk about it all day long, let's look at what I'm talking about. So if we want to calculate, say we don't know what this transformer is, and we're not, so we want to measure it, okay? You can actually put a known voltage into the primary, measure the output from the secondary, calculate the turns ratio, and then we can, from that, calculate the impedance ratio. Then we can figure out, with this impedance speaker on this particular terminal, what input impedance are we going to reflect back to the tubes. Okay, does that kind of make sense? I know I'm talking fast here, but it'll start to make sense as we test it. So if you look down here at this mess of wires, I have a power cord here, and it's going to the input, and let me see if I can find, here's a printout of the wiring diagram of this transformer, okay, from their website. And if you look, I'm going from this to this, okay, from the brown wire to the blue wire, which is the actual primary of this transformer, okay? So if you notice, I have my brown wire and I have my blue wire, and they're connected to a jumper cable that goes to a plug up here on my variac. And I have my variac set around 10 volts. You want a small voltage, and you don't have to have a variac. If you have a filament transformer with 6.3 volts, you can use that, okay? You're just doing a math formula anyways to figure out turns ratio. So I'm going to set it around 10 volts, and I'm going to measure the input. And then right now, I currently have this output second. This is an odd transformer. You actually have to wire things together to get your output impedance. On a standard output transformer, I don't know why Hammond does this. This is the weirdest thing. But bottom line is, you have to jumper wires together to get the different, 4, 8, and 16. On a standard transformer, you would have, you'd have 4 taps, 1 coil, you'd have the common, you'd have the 4, the 8, and the 16, and that's it. Why they do this, I don't know. I'm sure some of you may know why Hammond does this. It's just a big hassle because you can't easily change impedances from 4 ohms to 8 ohms on this without completely rewiring the transformer. And of course they sell, for a nice hefty price, a special switch that will let you turn the knob and it changes the taps, But who the heck wants to go through that? But anyhow. So, scenario is set. This represents the voltage going into the primary of the transformer. This represents the voltage coming out of the speaker terminals of the transformer. The transformer is configured right now as it is for 16 ohms. Okay, so that means it's configured if you were going to use a 16 ohm speaker, or 2 8 ohm speakers in series, or 4 4 ohm speakers in series, something like that. Okay. I flip on my variac, and if you look, I have 10.36 volts. Now it's really hard to get exactly with that variac, it's touchy, so that's as close as I could get it. But that's okay. We're just going to do a math formula. So I have 10.36, 10.35 going in, and if you notice, I have 0.706 volts coming out of that 16 ohm tap. Now what I've done here, you guys are going to like this, is I have a little spreadsheet that I made up, and by doing this measurement, I can type this in and it will calculate what I have, okay? I'm going to show you that in a minute, but first let's get our 3 measurements. So right now at 16 ohms, okay, on a 16 ohm tap, why is my pen always gone? Okay, here it is. So on the 16 ohm tap, I'm getting 0.707 volts. Okay? Keep that in mind. Now I'm going to shut this back off, and I'm going to rewire this mess for 8 ohms now. Okay? Okay, I've now moved my taps around here so that it's wired for 8 ohms, for an 8 ohm speaker. I'm going to turn on my variac once again, and once again I have 10.35 volts again, and this time on the output I'm reading, on 8 ohm tap, I'm reading 0.412. Okay, so there you go, 0.413, let's say. It's not super critical. Alright, now for the 4 ohm tap, all I have to do is move my probe because the wiring of the transformer is the same. So I go from this terminal to this terminal, and if I read that, I'm getting 0.292. And I have 10.3, let's say, I'm just going to call it 10.37 volts. It jumps all over the place, in. Okay. Now that we have that, we're going to go up to my little calculator. Alright, can you see that? I hope. Well, there's my calculator. Sorry about the angle here, but that's kind of where we're at. And I'm going to say that with an input voltage is 10.37, 0.37. And on the 4 ohm tap, if you remember, we measured 0.292. On the 8 ohm tap, it was 0.413. Right? And on the 16 ohm tap, it was 0.707. All right? And as you look down here, that gives us all of the things. Now, turns ratio is just V in divided by V out, okay? So it is a 35.5 to 1 turns ratio, okay? On the 8 ohm tap, it would be 25.1 to 1. See how it's figuring it out? Okay. And on this tap, it would be 14.67 to 1 turns ratio, okay? And then the impedance ratio, and I'll explain that in a second here, is your turns ratio squared. So you just take the turns ratio times the turns ratio, times itself, okay? And that gives us an impedance ratio of 1261, 630, and 215. Now, in order to determine what your reflected impedance to your tubes is going to be, we have to go ahead and calculate. If I put a 4 ohm speaker on the 4 ohm tap, I'm going to get about 5,044 ohms. So if you notice, this was rated as a 5,000 ohm transformer, and that is your 5,000 ohms. And if you look at 8 ohms, it's 5,000. If I have an 8 ohm speaker on the 8 ohm tap, 5,000 ohms. The only place it starts to tail off a little bit is if I go a 16 ohm speaker on the 16 ohm tap. I'm a little bit lower than that, okay? And part of that could be my meter. Part of that, you know, if I put higher voltages in there, maybe it would, you know, the losses wouldn't be as much. I don't know. You transformer guys out there, electrical engineer, physicists, can figure that one out for me. But bottom line is, that's what it is. But these other columns are the really important ones, because now I can see if I have a 4 ohm speaker, by changing what tap I hook my 4 ohm speaker to, I can change the plate resistance to my tubes. And that's extremely important, because the plate resistance is going to really determine what kind of load, watts wise, you know, of current, what kind of current you're going to draw through that tube, okay, or through those tubes if it's push-pull. So in an ideal world, you hook the transformer up the way it's intended, and you get the advertised impedance, and the world is good. But my problem is I don't have a 450 volt power supply. My power supply is going to be closer to, you know, 375, 380, somewhere around there. I don't know. Okay, it's going to be in the 300s. It's going to be almost 100 volts less than my tube data sheet is asking for. So that being said, if I put that lower voltage on my tubes, everything will work, but it will dramatically reduce the output to the speaker. Okay, so however, if I use a different tap at that lower voltage, it's going to draw heavier current, but at the lower voltage, the overall wattage through the speaker or through the tube will still be good. Okay, will be within spec of my tube. And now this is where you have to use your tube data sheets, in that, you know, for instance here, something's beeping. Oh, my meter. There we go. So going to the tube data sheets, come on and focus. There it goes. If we look at those, you can see it gives you an idea of what current that tube can draw. The other thing that you can do is if you go to the maximum ratings, alright, let me see if I can find that sheet for you. If I go to the maximum ratings here, sorry about that. So if we look at the maximum ratings, it shows that the design maximum values is they want no more than 450 volts on the plate, but it can be less. And they want a total plate dissipation of 30 watts. So what that means is that to a certain degree, if you reduce the voltage, you can increase the current through that tube a little bit, as long as you don't exceed that 30 watts. And this has to be within reason. You can't go to extremes, okay? So, for instance, what they're talking here, at 350 volts on a... where are we at? They don't have the plate right here. Load resistance is 4,200 ohms, okay? You should get about 10.8 watts of power at 15% distortion though, okay? But we can play with those numbers, and we can, that's for a class A amplifier, of course, but if we go to class AB push-pull, which is 2 tubes, 6L6 and 6L6GC will work the same. It's just this one has higher maximums than this one. But again, if you look, if I put 360 volts on the plate on a 3,800 ohm plate-to-plate resistance, okay, I can get 18 watts. But I can also, if you notice, if I use a higher impedance ratio transformer and get 6,600 ohms on plate-to-plate, that power goes up to 26 watts. You see how that works? Same amount of voltage, but just by changing that load resistance of your primary of your transformer, it's changing the performance. And the reason being is you're changing the ratio of your turns ratio, so you're putting a higher voltage out of that speaker terminal across your load. So you can see we can play around with these numbers that we have over here, and we may be able to, even though it sounds unconventional, I can actually, we're going to sit down and look at these combinations. So if I take a 4 ohm speaker, and if I have this plate resistance at a certain current, as long as I don't exceed that maximum wattage of 30 watts for a 6L6GC, it should work, even though it's a lower voltage than the 450. Does that make sense? It's just a balancing act. It's kind of like Ohm's law, you know, when the watts is going to stay the same as long as the ratio, that ohms or volts to amps, gives you the same product. Okay, so 1 amp at 10 volts will give you the same wattage as 10 amps at 1 volt. Does that make sense? 10 times 1 or 1 times 10. Okay, so it's just, that's all we're doing. So let's look at this right here is where I'm interested in, is using a 4 ohm speaker on the 8 ohm tap with a lower plate-to-plate voltage and see what's going to happen to our current on our tubes. Okay kids, don't try this at home. What I have is kind of a simulated amplifier setup. And what I mean by that is I am pretending that I have a couple of tubes connected to the primary of this transformer, and I'm going from plate to plate. Okay, so the peak voltage from the center tap to each plate is going to be half of our test voltage, if that makes sense to you. So when we see 100 volts plate to plate, that would be the same as if we had 50 volts applied DC to the center tap and we're driving it to full 50 volts on either side, positive and negative, if that makes sense to you. So anyways, I have it connected to the Variac. I am on the 4 ohm tap, and I have a 4 ohm resistive, DC resistive load connected to the output. And I have this milliamp meter, which is an AC milliamp meter, in line with the primary of this transformer. So in other words, we have the Variac connected through this meter, and this meter is reading the voltage, okay, across the primary. And then this is monitoring, when it stays on, this is monitoring the actual voltage coming out of the transformer into my simulated speaker, my 4 ohm load, okay? And when we increase the voltage here from the transformer, or from the Variac, I'm going to put 100 volts in it, and you can see I'm up to 89. And guys, don't try this at home unless you know what you're doing. Please work safe. If you do this, you're doing so at your own risk. Hate to use that term, but I can't think of better words chosen for this. So we come up, and like I said, this Variac's very touchy. Okay, and we're at 99. There we go. About 100. Come on down. Just a teeny little bit. That's about as close we're going to get it. So I have 100 volts, or 100.3 volts, let's say. So there's 100 volts going in. With 100 volts on my primary, again, plate to plate, I'm drawing about 19 milliamps of current. So that would be the current flowing through the tubes if the tubes were in there. Now, there's an awful lot of other things. The tubes themselves dissipate energy and so forth, so let's not get into all that right now. I'm just trying to see where we're going to be based on my power supply that I'm going to put in there. And you can see the output of this is about 2.7 volts going into a 4 ohm load, okay? And so if we do the calculations, if we have 100 volts and we have 19 milliamps going in, we're going to have 2.7 volts into 4 ohms, which is going to come out to 1.8225 watts, okay? So about 1.8 watts. And that's going to equate to about 675 milliamps through this. So I have 2.7 volts at 675 milliamps out, okay? So why am I doing all this? I'm doing this because, again, I'm not going to have my 450 volts from the RCA tube manual. I just want to get a feel for, if I use this transformer here and I do, I do the 275, 0275, that's going to give me approximately a 375 volts or so output. Is that going to be good enough to drive this amplifier properly if I bias it properly? And the answer seems to be right now yes. Okay, I can stay within tolerance. Basically, at 375, that's 3.75 times, and everything's linear. When if I drop the voltage to half, my current's going to cut in half. So if I go down to 50 volts, I should have about somewhere around 8.5 or something, right? Or I'm sorry, 9.5. And you see right there, 9.5 at 50 volts. So it's linear. So that being said, if I have 375 volts, okay, that's 3.75 times the amount of voltage that my 100 volts, okay, times, and everything's tracking on the other end too, times my 20 or my 19 milliamps. Wait a minute. 3.75 times 0.019. That's 19 milliamps. is going to give me 71 milliamps, okay? And 71 milliamps would be flowing through each tube, okay? So if I look on my tube charts, now I have that, right? So let's turn this down, turn this off. So that's going to give me 71, I'm writing this down, 71 MA per tube. If we go back to our tube chart here, and I'm kind of doing this to show you guys the relationship of how this all works. There we go. Class AB1. And you can see for two tubes, values are for two tubes, they want at 360 volts on a regular 6L6, it can do 140 milliamps. And on the GC, even at 450 volts, I can do up to zero signal plate current, idle current can be 116 milliamps, okay, and 210 maximum signal, okay. So if I do my 71 and 71, that's going to be 142. So even for a 6L6, I'll be pushing it, but it'll be pretty close. So what this is all saying is it's going to make sense, okay? We can play with our bias adjustment and with those voltages, and we can get near the power we want with that lower voltage just by playing with the bias and still not exceed the limits of the tubes. I hope that's kind of making sense to you guys. Probably if you misunderstand, you might think that I'm saying something wrong, or you may not just know what the heck I'm talking about at all. But bottom line is, you see from how we're using, how we have everything set up, you can see the interaction between voltage and current and the turns ratio and the impedance ratio of the transformer. Now if I switch this over, for instance, I put that same 4 ohm load onto the 8 ohm tap, let's say, okay? So we're going to go to 8 ohm tap. I'm going to show you how this changes everything. So everything is now staying the same, right? So all I changed was I just put my load across. It's still a 4 ohm load, but it's going across the 8 ohm tap instead of the 4 ohm tap. So we've just effectively, according to my chart, changed that transformer impedance to 2,541 ohms instead of 5,044 ohms, okay? Now watch what happens as I turn the power up now. You're going to find out the input's going to change a little. The voltage will be the same, but these guys are all going to be a little bit different. So look what's happening now. As I go up to my 50 volts, okay, you see there? There's 50 volts, and at 50 volts now, I'm getting almost the same current through there that I was at 100 volts when I was connected to the 4 ohm tap. And my output voltage, instead of 2.7 volts now, at 100, I'm getting about 1.8 volts at 50 volts. So as you can see, it makes a huge difference. So let's go all the way up to 100 volts and do apples and apples. Okay, and yes, this transformer can handle it. Okay, so come on down, this thing's so touchy. Okay, 100 volts, okay, so I've got 100 volts going in. Now at 100 volts, I have 100 volts. I'm drawing 36 milliamps. Okay, and my output now is 3.6 volts, okay, into 4 ohms. And if we do our little calculation, I have 3.2 watts, which is not quite double, okay? 3.24 watts. And that's 0.9 amps, which is, 900 milliamps. So, and you can see all I did was just connected it differently. But you see how much more draw now it's putting on. From 19 milliamps at 100 volts, I'm now 35.9, 36. Okay? So I'm almost, but not quite, almost double the current draw through. So I'm basically getting more power out to my speakers, but in the same token, I'm also putting a lot more load on my tube. Does that make sense? If that tube was in line where this meter is, this meter represents what my tube is going to be seeing, roughly, okay, in the circuit. So the point that I'm trying to make, guys, is that when you put the wrong load onto your output terminal, so you hook a 4 ohm speaker onto an 8 ohm terminal, this is what it's going to do to your tubes. Does that make sense? Now sometimes if you know what you're doing, you may want to do that. Let's say the transformer impedance doesn't quite match the tube that you're connecting to it. Well, you can do things like this and purposely put a heavier load on the tube to get more wattage out of your amp. It's not, as long as it doesn't exceed the limit of the tube. Okay? In this instance, if I put 3.75 times that voltage on there, and this goes up by 3.75 times, I am way going to exceed the power of that tube, the dissipation of that tube. Okay, that tube is going to basically fail pretty quickly. So once again, we know now that we can use this transformer. We can use that 375 volts or so of power. We can bias the current in the tube a little bit hot because of the lower voltage and still be able to get out, 40, 50 watts from this transformer. And that's what all this is all about, this whole exercise, okay? Now, of course, we can just calculate all that from our little chart, but I wanted to actually give you a visual representation. And I've actually never rigged anything up like this before either, so I kind of wanted to see how it all tracks, just physically see it. So the good news is we have an output transformer and we have a power transformer now for our bass amplifier project. Okay, and we know that we can use some 6L6 GC tubes, and we could probably, if we keep everything right, use the 4 ohm tap and use the with a 4 ohm speaker. We could even probably just tweak down the bias just a little bit, and we can even use those 5881s or 6L6s, 6L6Gs, the smaller powered 6L6 family, and get a little bit lower power amplifier just by changing bias a little bit. So this is going to be a pretty versatile little amp. I think it's going to work out pretty good. There's I can go on and on about guitar amplifiers. I mean, there is a huge difference between an audio amplifier that you listen to music on and a guitar amplifier that you play an instrument through. Because once again, I believe, and I'm of the camp that believes, that the amplifier is just as much of an instrument as the instrument itself is. Because with a bass amplifier, I don't want it to distort. I want a clean sound. So that's why I'm going to use diode rectifiers and use a solid, strong power supply. I'm going to bias this thing so it stays within its happy place and doesn't go into distortion. But if I were building this amp for a guitar, none of those things may not be desirable, because the thing that gives the guitar its sound sometimes is the amplifier distorting, and you're purposely causing that. Some people even purposely put too small of a power supply. It's called a soft power supply that'll help the amplifier to break up a little bit and distort at lower levels. You know, that's that's just completely unheard of in the, you know, in the audio field when you're listening to music. That's the biggest no-no in the world. But with guitar, it changes the shape of the sound. It gives it that distorted sound that, you know, that is very unique to a guitar, to an electric guitar. So anyhow, that's enough of a rant about that. But I'm going to get this video posted. This is going to be part 1 of the vacuum tube bass amplifier project, and the next part is going to be choosing a suitable circuit design and kind of laying it out, kind of like we did on our guitar amp project. And oh yeah, I still have the guitar amp. I just haven't had a chance to get out in the shop and do any woodworking to make a cabinet for that thing. What I think I'm going to do is wait till this project's done, and then maybe I'll probably go out there one day and I'll knock out 2 cabinets, you know, one for that and one for this at the same time. My shop's a little bit of a mess from some projects we was working on earlier, so it needs cleaned. So there you have it. But I hope you learned a few things here just tinkering around. I hope you did too. I hope I didn't sound too crazy, and I hope I didn't do anything wrong to mislead you guys. I'm thinking I'm on the right track here, but you never know with Tony, huh? Anyways, you all have a wonderful day, a wonderful afternoon. Glad you came along to watch, and part 2 to come later.